So let's look at ionic bonding. So potassium. So if we write the Lewis symbol for potassium, the element symbol is capital K. How many valence electrons does potassium have? One. It's in group 1, right? Here we have the electron configuration for potassium, and we see for valence electrons, we're looking for the highest principal energy level, so that would be 4. And how many electrons are in that? 4. It could be sp or whatever. There's only 1, so 1 valence electron. And chlorine, symbol capital C, lowercase l, how many valence electrons? 7. So 7 means there's going to be pairs on 3 sides and a single electron on 1 side. So 7, right? What do the atoms want to achieve? How many valence electrons? 8. They want 8. So here's chlorine. Chlorine's got 7. She's pretty anxious to just get 1 more electron, right? And so she's looking around, seeing who is willing to give her an electron. Here's potassium. And we might look at this and say, well, potassium's looking to gain 7 electrons. But when we look at its electron configuration, if we get rid of this valence electron, that outermost shell, that little, I've told you before, these shells are a little bit like onion skins, right? So this is a partial onion skin layer. And so if we took that off, what's underneath? An intact, full onion skin, right? So if we take this valence electron off here and make a positive ion out of it, 4s0, then these are now become the valence electrons. How many are there? 8. So instead of gaining 7 electrons, potassium can get an octet by just losing 1. So potassium's looking to lose 1 electron. Chlorine's wanting to gain 1 electron. Some matchmaker brings them together, and they're like, oh, cool, we can fulfill each other's wildest dreams, right? And so the potassium will give its electron to chlorine. So we'll take that away and give it to chlorine. Now, when that happens, we have ions because they don't have an equal number of protons and electrons anymore. So this is a positive potassium ion, and now this is a negative ion. Positives and negatives attract, and so they form an ionic compound. You can imagine with all these dots all over the place that this minus sign could kind of get lost in the dots. And so what we generally do is we put brackets around and we put the charge on the outside. It's just a convention. Potassium lost an electron, but we don't want to suddenly start drawing electrons that were core electrons before. When we do Lewis structures and we move electrons around, we have the same number of dots at the beginning and the end. We're not going to have any showing up or disappearing. And so instead of drawing 8 valence electrons now around potassium ion, we just understand that we took off that outer layer that was just a little bit, and underneath is a full layer. And so we'll get an ionic bond that forms between these two. Any questions? So let's do an example. Let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. Now, we learned to do this based on charges and stuff, but we're going to use Lewis symbols to do this. So we've got magnesium and we've got nitrogen. So the Lewis symbol for magnesium, we've got Mg. And how many valence electrons does magnesium have? 2. So we're going to have 2 dots. And then we've got nitrogen. Let's make nitrogen green. So nitrogen, capital N. And how many valence electrons does nitrogen have? 5. So 1, 2, 3, 4, 5. We want to get at least one electron around on each side before we pair up, but there's 5. Okay? So the nitrogen wants to get 8 valence electrons. It could either lose 5 or gain 3. But it's a nonmetal, and what do nonmetals do? They gain electrons and form negative ions. Nonmetals make negative ions. Magnesium is it's a metal. Metals tend to form cations. It would either lose the 2 electrons or have to gain 6. So what's easier? It's easier to lose 2. It's the closest. So magnesium's wanting to lose 2 electrons, nitrogen's wanting to gain 3 electrons. So this is where the atoms start talking to each other. So the nitrogen says, hey, could you give me your extra electrons there, those valence electrons? I know you would like to get rid of them because there's just this messy partial outer shell. The magnesium says, great, take them, please. So we move those over. So magnesium is going to get rid of those 2 electrons and give them to the nitrogen. Now, magnesium has a charge, doesn't it? It lost 2 electrons, so it's got a positive 2 charge. Is the magnesium happy? Yeah, it's got an octet. We're not showing it in the symbol, but under those 2 valence electrons, there's a nice complete shell of 8 electrons. This nitrogen now also has a charge. What's the charge on the nitrogen? 2 minus. Is the nitrogen happy? No. It's happier, but what does it need? 1 more electron. Well, if there's 1 magnesium atom around, there's probably a whole bunch more. So he got 2 electrons from 1. Now he's going to go looking for another magnesium. So let's bring in another magnesium. So here's another magnesium. And this one also has 2 valence electrons. So nitrogen says, hey, can you give me one of those? And magnesium says, sure. Do you want both of them? And nitrogen says, no, I just want 1. Magnesium's like, well, that's better than nothing, right? So gives 1. Now the magnesium has a charge of +1, and the nitrogen has a charge of 3 minus. Right? So magnesium ion over here is happy. Nitrogen's happy. Is this magnesium happy? Nope. Needs to offload 1 more electron. Well, who's around to take them? Nitrogen. So we got to bring in another nitrogen. This nitrogen also has 5 valence electrons. And so magnesium is like, hey dude, take this electron. And nitrogen's like, great, I'll take that. Can I have more? No, I only have the 1 I can give you. Well, better than nothing, right? So we take this electron from the magnesium and give it to the nitrogen. And now we've got charges, don't we? This has now a -1 charge, and the magnesium has a +2 charge. Magnesium's happy. Nitrogen's working on it, but not there yet. What do we need? 1 more magnesium. Okay, so let's bring in 1 more magnesium, also with 2 valence electrons. Nitrogen, hey, give me those electrons. Magnesium's like, oh, I'd be happy to. You want 2 of them? Yeah, I want 2. So we get rid of these and give them to the nitrogen. Oops. Now this magnesium has a +2 charge. It's got an octet of valence electrons because we removed the outer level, and underneath there's a full level of 8 electrons. This nitrogen now has a charge of 3 minus, and it has 8 valence electrons. So it took 3 magnesium atoms and 2 nitrogen atoms for them to come up with the right ratios so that they could share electrons and everybody could get satisfied. So to write the formula for this compound, we'd look at, well, how many magnesiums are there? Well, there's 3. So Mg3, and how many nitrogens? 2. Mg3 and 2. We get the same result is what we learned in an earlier chapter, where we would look at the two elements, and from position on the periodic table, we would predict that magnesium has a positive 2 charge, and nitrogen has a 3- charge. And then we'd look at their charges and either do some mental math or do the crisscross thing, and we'd end up with this same formula. This does a better job of explaining why it works out that way. Any questions? When we look at the formation of ionic compounds, it's usually quite exothermic. It happens very spontaneously and releases a lot of energy. When sodium metal reacts with chlorine gas, it forms sodium chloride, and the heat of formation of this is minus 411 kilojoules per mole of sodium chloride formed. Okay, so we measure that experimentally. If we look at ionization energies and electron affinities, in order for sodium to become a sodium plus ion, we have to remove 1 electron, and that requires an ionization energy. So to form the +1 ion, we have to give this 496 kilojoules per mole. Metal atoms lose electrons easily, but they're not giving them away. You have to pay them a little bit of energy to get the electrons away from them. It's just that it's pretty cheap. If you're trying to take an electron from a nonmetal, don't even bother. It's going to be very difficult to do that because the ionization energy is very high. The electron affinity for nonmetals is negative. So when you give them an electron, they will pay you in energy. So making chlorine into a chloride ion releases 349 kilojoules per mole of energy. So if we have sodium, 1 sodium ion, or 1 mole of sodium forming and 1 mole of chloride forming, we could add those together, and what we get from here is that the transfer of an electron from sodium to chloride actually absorbs 147 kilojoules per mole. But we know experimentally when we do this that 1 mole of this is going to release 411 kilojoules per mole. So there's got to be something missing, right? I grew up listening to Paul Harvey on the radio. That tells you how old I am. But he would start telling this story, and then there'd be a commercial break, and then he's like, and now for the rest of the story. And then be kind of like the punchline of the story. So this is lattice energy, the rest of the story. The guy that wrote the book is old like me. So lattice energy is what explains this discrepancy. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. And this is from the ions in the gas state. So potential energy is lowered when opposite charges come together. So you've got sodium ions and chloride ions. In order to make those, you had to put energy in. But now that we have these charged particles, when they get close together, their energy becomes lower, and what happens to the energy that they had? It gets released. So the energy is released as heat. So the formation of ionic compounds is not exothermic because the metal wants to lose electrons and the nonmetal wants to gain an electron. We talk about it that way. The reason it's exothermic, the reason it happens is because when the cation and the anion come together, when they coalesce to form a lattice, it releases a great deal of energy. It's like playing with magnetic building toys, right? You get those pieces close together and they just stick, right? It just happens because of the magnetic attraction between opposite poles of the magnets. Ionic electric charges are a lot like that. And so positive and negative charges will stick together just like magnets do. And when that happens, it releases energy. That make sense? So here we have an illustration of this. Sodium ions and chloride ions. As these come together, remember the energy is proportional to the magnitude of the charges divided by the radius. So the closer they are, the smaller the radius, the more negative the energy is. Negative energy means it's releasing energy into the surroundings. So as these come together, their energy is lowered and they release energy into the surroundings as heat. That release of energy is the lattice energy. So we have to put some energy in overall to form the ions. But then when they come together, it releases more energy than it required. So this brings us to an idea called a Born-haber cycle. It's named after a couple of scientists. And this is the easiest way to calculate lattice energy. So a Born-haber cycle is a hypothetical series of steps representing the formation of an ionic compound from elements. And this makes use of Hess's law. So Hess's law says that if we can write chemical equations that we can add together to form the overall reaction, if we know the heats of reaction for those individual steps, we can just add them together and find out what the overall change in enthalpy is. So what we're going to do is we're going to utilize Hess's law, and we're going to choose steps here for which the standard heat of formation is known. We must also know the overall change in enthalpy in order to be able to calculate the lattice energy. Okay, so here's an illustration of this for the formation of sodium chloride. So we're starting here with sodium atoms and chlorine molecules. And when those come together, they form sodium chloride, solid, and there is a release in energy. That is the heat of formation for sodium chloride. Remember, a heat of formation is the heat of reaction when you make 1 mole of that compound from the elements in their standard states. So the standard state for sodium is a metal, pure metal, solid. For chlorine, it's Cl2 because it's a diatomic element, and it's a gas at room temperature. So that's its normal, lowest energy state. So we can measure this enthalpy change. We can measure the ionization energy and the electron affinity, and we saw that those did not add up to this at all. So instead of looking at ionization energy and electron affinity, we're going to look at a series of reactions where we know what the enthalpy change is. So we're going to imagine we're going to take this sodium and we're going to put it into the gas state. People have studied that. You can look that up in a table. And so you can find the heat of the standard heat for that. Then we're going to take the chlorine molecule and separate it into chlorine atoms. That requires energy. We can also look that up in a table. So we can find the standard heat for this second step. Then we're going to make the sodium into an ion. As we're going up, we're having to put energy in. So we're putting energy in. You have to exert energy to climb up a hill, right? We're climbing up here, and we're making this sodium ion. And so this would be the ionization energy of the sodium. And then we're going to make the chlorine into a chloride ion. Well, that's actually a negative. So that's releasing energy. So we're starting to come back down. Now we've got the sodium ion and the chloride ion. And when those two come together, they're both in the gas state. When those two come together and form the sodium chloride compound, it releases a great deal of energy. And this change in energy here is the lattice energy. It's the energy associated with the formation of a compound from the ions in the gas state. We can calculate this by knowing all of these other steps. So we know that this number plus this number has to add up to the sum of those guys. Does that make sense? So we're determining it in an indirect way. And we can do this because the change in energy for these things is a state function. It doesn't matter how you got there. And so it's like, measuring a distance. If you've ever done any building or anything, you may have encountered something like this, where you've got this distance that you need to measure, but the arrangement is such that you can't get a ruler in there or a measuring tape or anything in there to measure it. But maybe you can measure this distance and this distance. Whoops, that's not very good. And this one. So if you know, we'll call that x, and you know y, and this is maybe z, you know that x is equal to y plus z. If you know x and you know y, then you can find z, even though you can't measure it directly, right? That's what we're doing here. We're looking at steps that we know, and then we have this one step that we don't know, and that's the lattice energy. Any questions? Of course, there are trends in lattice energies. One of the things that affects lattice energy is the size of the ions. We learned in Chapter 8 about trends in atomic and ionic sizes. So if we look at different metal chlorides, lithium, sodium, potassium, and cesium chloride, what's similar about these compounds is that they all have chlorine as the anion. What's different is they have different metals, but all those metals are in the same family. They're all in group 1. So we can predict the relative sizes of those ions, right? Lithium's going to be the smallest, and they're going to increase in size as we go down to cesium. We're comparing them with, all of these have chlorine, and so the chloride part is staying the same. The only thing that's different is the size of the cation. When we look at the lattice energies, we see that the lattice energy for lithium chloride is larger than for cesium chloride, and there's a trend. Why does this happen? Well, the lattice energy, remember Coulomb's law, the lattice energy, the force of attraction between the oppositely charged particles is inversely proportional to the radius, the distance between them. So the further apart they are, the lower the attraction. So this being a larger negative number, these ions must be able to get closer together than the cesium in the chloride. And that's because of the physical sizes. So cesium is a larger ion. And so the nuclei, the distance between the nuclei here is larger than for lithium chloride. So for lithium chloride, those oppositely charged ions can get closer together, and so they have a lower energy, a more negative energy. Any questions? Ion charge also affects this. So here we're going to compare sodium fluoride and calcium oxide. So the reason we chose these two to compare is that the bond length, or the distance between the nuclei, is very similar. 239 picometers, 239 picometers, very similar. But the lattice energy is very different. For sodium fluoride, it's minus 910 kilojoules. For calcium oxide, it's minus 3,414. That's a lot more. Why? Has to do with the charges. Coulomb's law says that the energy is proportional to the charge on one times the charge on the other. So sodium is +1 and fluoride is -1. So here we have Q1 times Q2 is +1 times -1, and so that equals -1. Calcium's +2 and oxygen's -2, and so here we've got +2 times -2, which gives us -4. So that top part of Coulomb's law, Q1, Q2, is 4 times as large for this compound. And we look over here and we see that, 3,400 is roughly 4 times larger than 900. So the magnitude of the charges affects the lattice energy. So lattice energies become less exothermic, meaning smaller, closer to zero, as the ionic radius gets larger. Lattice energies become more exothermic, larger negative numbers, farther from zero, as the magnitude of the charges increases. So if you've got plus 2 and 1, that's going to be larger than plus 1 and negative 1. Okay, so this is the sort of thing you might see on a test. Arrange the following in order of increasing magnitude of lattice energy. Remember, when you're asked to arrange something in order of increasing, that means you start with the smallest, and then you go to the next biggest, and the next biggest. You end up with the largest. Okay? So we've got lithium bromide, potassium iodide, and calcium oxide. So let's look at these individual ions. So lithium bromide, we've got the lithium ion is +1 and bromide ion is -1. And potassium iodide, we've got K+ and I-. And calcium oxide, we've got calcium is +2 and oxygen is -2. So we're going to look at charges and sizes. So which of these compounds has the largest charge product? This one. We've got +2 times -2. This is going to be -4. This is -1 and -1. So that's the charge is much larger. Higher charges, does that make the lattice energy larger or smaller? So it depends on how you define smaller. So we're dealing with negative numbers here, and so that can be confusing because we think of a larger negative as sometimes being smaller. But negative means that it's the energy being released. So if we have -4 versus -1, -4 is a larger negative number, meaning more energy is being released. Does that make sense? You kind of have to be able to just think that out because it can be very confusing. So we're thinking this one's looking like a good candidate for largest lattice energy, right? This is the highest charges. Well, how could we decide which of these should be the smallest lattice energy and which one was going to go in the middle? Because their charges are the same. We're going to have to look at sizes. So we've got lithium and bromide. So here's lithium. There's lithium. And here we've got bromide. And then I'll do this in a different color. We've got potassium and iodide. So is lithium larger or smaller than potassium? Smaller. So this one's smaller. And over here, bromide and iodide, which one's smaller? Bromide, right? The elements at the top are smaller than the ones at the bottom. So lithium and bromide are the smallest, and potassium and iodide are larger, right? So these are the smallest, and these are larger. I guess I should call that smaller and larger. Do we care about the sizes of calcium and oxygen? Not really, because the difference in charges is such a huge factor that the sizes then aren't going to matter very much. And if we look at the sizes, calcium here right next to potassium, so those are going to be fairly similar in size. Calcium's going to be a little bit smaller. And up here is oxygen. Oxygen's smaller than both of these. And so that trend in size isn't going to mess anything up. So look at the charges first. That's the biggest thing. And then when you have things with equal charges, compare the sizes. So smaller ions, is that higher or lower lattice energy? Larger or smaller, I should say. it's a larger larger lattice energy, because those charges can get closer together. And so the closer together they can get, the more energy they will release. So that's the smaller size, but this is, I don't want to do that. Where shall I put this? I'll put it over here. So calcium oxide has the largest lattice energy because of its charges. And then we're comparing these two and seeing that this is larger ions, so they're farther apart. They can't get as attracted to each other. Another way to think of this is kind of silly, but you got two people, a guy and a girl, and they went to the North Pole, and they're like all geared up for really, really cold temperatures. They got parkas on and scarves, and all you can see is their eyes, right? How much physical attraction can there be between these two people? There can't be much. They're just two blobs of polar tech or something, right? Here you've got two people. There's smaller clothing. These guys are on the beach in the Caribbean. He's got a Speedo on and she's got a string bikini. There's going to be more physical attraction, right? Because there's less between them. Does that make any sense? I don't know. So this is the bigger attraction. And so we're going to put that one in the middle. And the potassium iodide has the smallest amount of attraction. It will release the smallest amount of energy when the compound forms. Any questions? So let's look at how this idea of ionic bonding explains properties that we observe in ionic compounds. We observe that ionic compounds have high melting points. Have you ever melted salt? No. It's because it's pretty much impossible to do at home. So don't try that, because you'll burn up your frying pan if you try that. You can melt salt, but it melts at a really high temperature. And that's because the ionic bonds that hold the sodium and the chloride together are really strong. Part of the reason that it's so strong is that those bonds are non-directional, meaning the force of attraction is not just between these two ions, but any given ion is also attracted to all of the oppositely charged ions around it. And so they are very, very stable, so high melting point. Ionic compounds do not conduct electricity as pure compounds. A crystal of salt will not conduct electricity. But if you put the salt into water, it will conduct electricity. Because when you dissolve an ionic compound in water, you separate the ions. Now you have positive ions and negative ions separated in the water, and they are free to move, and they can conduct the electric current.